Hi everybody, this is another Bluetooth type speaker, wireless speaker from Cambridge Audio. It's the Minx Air 100 wireless music system from Cambridge Audio. Very expensive, no doubt. It's got little rubber buttons on the top. Bit cheap feeling, to be honest, in this day and age. I think silicone, I suppose they are waterproof probably. If they're sealed then that's okay. Anyway, listen. So yeah, Cambridge, very nice unit. I've got the electronics out of it at the moment, but you can see this is the back panel there. In the corner of a look at her rear, then she is. That's the one we're talking about. Clearly it's got no plugs and socket in it because all the gubbins are out on my table. I got down and dirty with her earlier on. Okay, so that's the thing that we're going to fix, and we just turn it over. There's something amusing here. This always gives me a thrill when I do something, is when I pull this off, if I can get it off. I didn't disassemble this. I was given this in pieces at the Repair Café when they decided it wasn't a fuse that was blown, it was something slightly more serious. Oh, I can get the lid off. The thing's eating its own panel. There you go. So here we go. Look what it says. Zoom in. No user serviceable parts inside. You want to bet? Let's see what we can do. Hey, look at those sexy speakers. Look, they're flat. I should have thought if flat speakers were the thing to do, that everyone would have done them by now, wouldn't you? That must be cheaper to make than Coney speakers and such. Anyway, so look, anyway, it's not working, and so I'm going to put this to one side at the moment because it's kind of irrelevant. What the user said was, and what we witnessed was, when you plug a power in, you can hear this ticking noise. It goes tick, 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 ticks, like something like a sounds a bit like a relay clicking inside. So either we've got a serious power short or we've got a fault in the power supply. So I'll just put that to one side. It's very heavy actually. It's got a reassuring amount of mass to it. So let's have a look at the boards. The boards. Look at the power supply first. Right, so the power is connected, not turned on. I've got this notepad here just stopping the two boards shorting together because this is high voltage, this is logic. Don't want that to be shorting together. Not good. So if we then power it up, we might get an idea of an inclination of what's going on. And then can you hear that clicking? Rhythmic clicking. I think you can. And interestingly enough, there's no flashing lights or anything else, so that's the problem. As reported, so at least it's not working, which is a good thing in the sense that we've got a hard fault. Just going to give it a quick scan with the thermal camera to see whether anything is getting hot. No, it's all cool, I think. You can't really see that very well because it's not responding to the screen very well. But you'd see some red dots flying up there, showing up. So there's no hard short or anything particularly powerful going on, it's just some kind of connection issue or power supply issue. Now if we just okay, let's have a look at this power supply from this Cambridge Audio radio. Here she is in her grandeur. Says high voltage, do not touch. Nah. Anyway, it's going to make me touch it. Don't touch when turned on, it should say. So what have we got here? Nicely made. I'm not sure I like that. Look at that. That's not good, is it? You can see that device there rocking on the. If I designed this, it wouldn't be like that. Watch. See? I wonder if those legs have come loose yet. And something's got to give, isn't it, if it does that? Don't like that. That's nasty. And the other thing, can you notice the other thing? Can you see anything else? I can. Look. Design fault. Cambridge Audio. Pair of tweezers. My life for a pair of Tweezingtons. Look. A nice long screw pushing into the back of the transformer. Pretty close to the windings there. Given it's the outside ones are normally the low voltage windings, or are they? But anyway, don't like that at all. Might reinforce that. That's not what our problem is, I think. Anyway, we've got this clicking issue. So, for those of us who, should I say, are not familiar with switch mode power supplies, let's have a quick look at this. Let's have a look at the landscape, the general landscape. It's a bit of a shame that this one's got those metal covers on, because it kind of cuts out the video and I'll tip up and show you what's inside. We've got the mains live and neutral come in at this end. Let's zoom in a bit so you can see a bit better. Mains, neutral and live go through a 3.15 amp fuse, go through some filtering beads here. That's just for HF filtering for conducted immunity from noise from the power supply being conducted out onto the wires and radiated by the mains wires. So I've no doubt this has been properly CE tested. Some filtering capacitors across the mains. There is a 471k varistor, very voltage dependent resistor, VDR. 471 is 300 volts AC. Come on, blimey. So that should clamp the mains round about 300 volts AC. It should start conducting. Yeah, I'd like to see, instead of a 471, I'd like to see a 371, which is 275 volts AC working, or it starts to conduct at 275 volts AC. Obviously the peak DC voltage is going to be 390 or something like that, but you can work it out. Anyway, that's a bit small. I'd like to see a bigger one than that in there, because anything more than a sparrow fart on the line, this will go up in smoke. So it'll do some arresting of the input voltage, but not much, and not until you get to 300 volts AC. And it is at 300 volts AC, it will start to conduct. It's not like a sudden high current clamp. It conducts better the higher the voltage go, or more conductive the higher the voltage, but it's by no means a straight cut off at the rated voltage. Okay, and they're slow. A very fast spike coming down here should be arrested by the capacitors rather than this, because this is very slow to respond to the it takes a while to break down and start conducting. So then you've got a dual mode choke here. That's just filtering live and neutral, so common mode rejection choke for noise coming in and noise going out. It'll block it both ways. Then another dual mode choke there, slightly higher frequency one, less turns. This one's quite a lot of turns on there, look. And oh, there's a transistor and a capacitor down there. We'll look at those later. They look odd. That looks like the body of a that's a very old transistor, isn't it? That package. Where can you see it? Can you see that one down there? What is it? What is it? What is it? It's a 2S. Those sorts of transistors, you've got a 2S B647. That's something like 80 volts, so it's like an 80 volt transistor. I don't know why they put that in there. We'll find that out. I mean, is it switching at 80 volts? Very old fashioned, but yeah, I'm sure it's fine. Chinese cheap transistor. You can buy those for a couple of cents each. They're so old and so common. So anyway, looking down here, back to this section, we've got, oh sorry, turn it around back the other way up so you are now familiar with the and then if we look in here, we have so you can see these two wires here going onto the heatsink. What do you think that is? I'll tell you what that is. That is a thermal cutout, and I've seen this design on many amplifiers and things, and it's just a resettable thermal switch bolted onto the heatsink with two wires coming out, so that when the heatsink goes too hot, these wires are normally closed connections in there. When the heatsink heats up and gets above the actual trigger temperature, these wires, the contacts open, these wires are no longer connected, and it's usually somewhere in the buck line or the bootstrap line for the power supply, so that when that gets too hot, the whole thing shuts down. Power is just stopped and no longer delivered anywhere. The whole thing will just go off, and when it cools down again, it'll come back on. So that's some kind of kill thermal switch, right? Now, on the main power supply, actually, is this the main power supply? What's the? Let's have a look at the other devices on here before I start pontificating about what's on here. Look, there's a chip down there. And you've got another buck transformer there. Not a buck. Yeah, no, it's not a buck transformer, is it? It's a switching transformer. And so you've got another chip down here and another transformer there. So it looks like there are two power supplies, two completely separate individual power supplies on here, because you've got one main power transformer here and one small power switching transformer and a, I don't know if you can see that chip down there. Can you see it? TNY274PN. So that's a Power Integrations, quite a modern, low-cost switching power controller. So it's got the FET, the switching power FET in there. It's got all the controls, all linked back to these pins. You can make a very low component count switch mode power supply. And it has to be said, to be honest, pretty unreliable too. These types of chips from Power Integrations, especially the LNK range, for example, God knows how many millions of tons of landfill they've caused by 50-cent component failing, and then the whole bloody contraption, whether it's a washing machine, tumble dryer, whatever it is, just gets scrapped because of that chip. Really bad. Not something you'd like to see in a quality piece of kit, to be honest. Certainly not in something you would want to be reliable. And this isn't a cheap bit of kit, it's radio. So what else have we got? We got a low voltage capacitor there, 47 microfarad, 35 volts. Got a normal fast diode. Ooh, no, oh yeah, 901 something or other. I'm assuming that's the main diode. 001. Seriously? Somebody hasn't read the data sheet, have they? What's that? Where is that diode in? That's terrible. Oh, I'm sorry, I'm ranting here. I'm just thinking out loud, actually. And then there's the capacitor there, which is just decoupling the input to this chip, I think. Oh no, sorry, that's part of the clamping circuit. I suppose you'd call it the snubber circuit, isn't it? So that small capacitor is part of the snubber circuit. That's part of the snubber circuit. Presumably this other diode here. What is that diode there? 6KE200. So that's a 200 volts DC transient suppressant diode, or transient suppressor diode, TVS. It's a TVS diode, a transient suppressor diode. I'll talk about that in a minute. So this hasn't got the conventional snubber circuit. This has got the TVS base snubber circuit, which is bad news actually. So there is a small power supply here, and the reason that quite a few of these modern pieces of kit have got two power supplies on is that they have to conform to the standby low energy rating. If you've got a device or an amplifier or a TV or whatever it is that's got a standby mode, the standby has to be less than 2 watts, typically 1 watt, and you couldn't run this big power supply on idle and power up all the electronics with that within that 2 watt budget for standby. So you have a power supply, a small highly efficient power supply in theory, producing a low voltage 12 volts or 5 volts, or in this case probably both. I'll see in a minute. And that supplies electronics in this case the radio music system to 5 volts or thereabouts to power up the standby circuitry and the IR controller, and just basically keep the micro running away ready to be switched on by the remote control, and you mustn't take more than 2 watts according to the legislation. It used to be an EN standard, but now it's common in the UK, and I think the Energy Star and stuff in America is very similar. If you want to know the standards, look up, but I always used to go on less than 2 watts on standby. So you've got 2 power supplies. You've got one there which starts up all the time probably, and you've got another one there which is kicked in to power up the amplifier and the power amplifiers and provide the voltages onto this board. I think if we look at the, I'm still plugged in, careful. If I look at the electronics, or the brains and amplifier board, you've got the voltages noted down here on the plug, look. So we look down here. I'll turn it around that way. You can see 26 volts and 5.6 volts, and a standby, it's STB standby line, and that will be the line that the micro uses probably to switch the power on and off on the board. So the question is, how's that going to work, right? Because if you look down this power supply, you have the, which end have we got? Yeah, we've still got the same way, but now all the bloody legends are upside down. If I turn it around, it's confusing. Mains is now coming in this end. What have we got down here? This is obviously the back of the board. Oh, yeah, we haven't mentioned that chip in there. There's the other power supply chip for this device, and let's see what it is. Top 249YN. So it's another one of these. A power integrations device. So it's a power integrations design, and I'll wager that this design has been taken pretty much straight off the power integrations data sheet. It's always a bad idea. So anyway, yeah, we've got 2 power supplies, one sub 2 watt one here, presumably providing the 5.6 volts, and there's another, what's that thing there? If we look on the back of it, can you work out what that is? Where are we? Where are we? We've got yeah. Oh, look at that. They must have run out of diodes on the line. It's actually got a wire-ended diode slugged across that. What is that? Is that the? Yeah, look, that's just there. That's the end of that black box device, and that is a snubber diode. So that is a relay. So you've got a relay, like a 12 or 5 volt relay, I'm not sure which yet, and 2 contacts there. That's the 2 contacts of the relay. If you turn it over, you can see underneath this part is the relay, that bit there, that black box. And what does that connect where to? So that track on there, this is a pointy thing, look, goes round here to, what have we got? Will it focus for me? You focusing thing? We have the main power bridge rectifier. It says AC in the middle, AC on the center 2 connections, look there, can you see that? And then minus and plus. So that relay, come on, focus your focusing thing, come on, thank you. Let's turn it around the way you had it, it's probably safer, isn't it? That relay here, those contacts, actually turns on the main AC line to the main power supply. So if that relay is open, the main chunky big power supply with the big transformer is switched off. So what closes that relay, we ask ourselves. So a bit more explanation about this. Look, you can see you've got, these are opto-isolators, where this is the isolation river, if you want to call it that. That's the isolation zone which prevents the switch mode power supply, which is referenced to the mains, so to the low voltage sides, which will be not directly connected to the mains. The only link to the mains should be, when you do the PAT test, is the inductance in the transformer. So there's no copper connection between the primary or main side and the secondary low voltage side, which is basically metal case. The electronics in the unit are not referenced to mains. There's no copper connection between the mains and the secondary side. So this is the 2K kilovolt isolation channel, which is what you do with a pack test. You put a high voltage on this side and you check to see if anything's leaking over to the consumer side, and the rules are that it's got to be 2 kilovolts or thereabouts. And you've got this space here, and in certain key areas where it does get a bit close, to improve the isolation you can machine a slot in the board. You can see there's a slot there, goes straight through, and that the idea of that slot is to stop moisture on the board or condensation on the board causing this to conduct across. So it's a bit close there, so they put that. Mind you, that blob of silicon won't be helping because that can get wet as well. So anyway, that's the isolation channel, and these are opto-isolators. So the low voltage side has got opto-isolators which have a photodiode in there and a phototransistor, and when you energize them, the photodiode, it shines light through across a gap, again a 2 kV isolation gap, to the phototransistor, which is a transistor on and off. So you've got 2 channels there and 1 down here. So this is the feedback for the main power supply, the one that powers the amplifier. One of these must be the feedback from the secondary to drive this power supply, powered by that TNY274 chip, and the other one must be to turn the relay on and off down here. So if you look down the mains, what's that thing there? Looks like, I think I know what it might be. Oh, it's looking pretty messy, isn't it? Got a gloop on it. Let's try and clean it off with a bit of the old love juice. There we are. Cleanliness is next to godliness. So my mum used to say on the bus while she was cleaning me up with a tissue and a quick wipe down before I went to Grandma's house after school. I'm sure that woman had dirty glasses. She used to rub away at my face, and I think it was just dirt on her glasses was the problem. So that is a yeah, it's a rectum fryer, isn't it? Look. So you've got a presumably a 400 or 300 volt AC working rectifier with AC, plus and minus. So if you put 240 volts AC on here, you'd get like 360 volts or thereabouts, 320 volts rectified. So you've got these power tracks, B plus power tracks, coming up to here. Which one's the positive? That's the positive one there. So this is the positive supply line, goes up there to the power transformer. And what's that there? Oh yeah, there's the class Y capacitor that goes between 0 volts or AC 0 volts, which is normally the neutral rail, and the 0 volt DC rail on the secondary side. It's basically can cut noise away from the secondary side down to neutral, which is more or less earth potential, but not quite. The next best thing to an earth is a neutral wire, but of course it's got all the power going down it, so it's going to have lots of noise. Anyway, where were we? Yeah, so we got power coming in here. It goes through the transformer primary. This one's not connected. Can't see if it's connected on that side. I'm guessing the primary of the transformer, the main switching primary of this small transformer for the standby power supply, is across those 2 connections, and you can that's borne out by the fact that look, there's our IC. Look, 1, 2, 3, 4 pins on one side and 3 on the other, and that's the actual drain for the FET. Source or drain? Source. Down here, where is it? There it is. That's that pin there. Look, see, it's got a pin missing to isolate from the high voltage from the 0 volts. So there we've got the yeah, that's the transformer connection. Now this must be a snubber connection, these components. What's that one there, I wonder? Something going from there to there and then from there to there, do you think? And what's that there? We just don't know, do we? Oh yeah, that's our class Y capacitor. That's the class Y capacitor between 0 volts, which is this rail. I know it's between plus rail. That's unusual. Go over the plus rail. I would always connect that connector capacitor across the transformer I guess it makes no difference, I suppose, but if it does, they're supposed to fail open, but if it fails short, you'd have a live 0 volts, wouldn't you? You've got a lot of faith in those capacitors. Quite often you see people put 2 in series in case one fails. That's be a really good design. In fact, I've done that before. You actually put 2 of those caps from the normal 0 volt rail to the 0 volt rails, and if you put 2 in, if one goes short, you still got the second one. You know, it just halves the probability of a nasty mains voltage getting out onto your DC rail on the secondary side. Now, what have we got? Anyway, this is why I'm boring you here. So we have got a... Okay, so this, don't forget, this is on the low side. We've got this channel here showing the low side, but in fact this is actually on the high side, isn't it? Because you've got bloody 300 volts coming in here. So this, someone's drawn that, the PCB layout guy has drawn that, but it's actually quite wrong, because this lot didn't need to necessarily be isolated, because this is at mains as well. But perhaps that's ground, this slot here. Do you remember that connector? That's ground. So you've got a ground track next to a 320 volt or bridge rectified mains, root 2 times the RMS value of the mains that's going in, basically 1.412 times 240. Yeah, so yeah, basically you've got full potential across these two. Everything to the left of these opto isolators all the way along there is on the live side of the board. Right, anyway, so power supply, there's your chip, look, then there's the connections, and you've got a 1 ohm resistor, and if this chip blows, always check the resistor, and that's a current sensing resistor. These TNY chips have got a few pins and a weird way of selecting the maximum current, and the maximum current is programmed by this resistor, I think, and the capacitor value. So it's a bit hit and miss, but the point is, this is in the return line from the transformer to ground, to AC 0 volts actually. So any current flowing through the primary reflects as a voltage across there, or galvanic voltage basically generated across the resistor, i.e. V equals I times R. So the voltage across this is proportional to the current flowing through it. The current flowing through it is through the transformer, so if at any stage, even on a single cycle, the current goes above whatever limit you've programmed by selecting these values during the design based on what says on the data sheet, if the voltage goes there higher on each spike, because remember this is a switching transformer, then it will immediately shut down the FET to stop destroying the device if you've got an overcurrent condition. And that also can be used during, obviously when you start running this, all the capacitors and everything else will be discharged on the secondary side, and so you can use it as a slow start, or what they call a soft start, to charge your capacitors up without taking too much current out of the power supply, and then the current will stabilize. But this is a low wattage design. It's got to be less than 2 watts, right? And then we've got a rectifier diode there from, so you've got a DC voltage from this transformer going out onto this side of the transformer for the low voltage isolated, but also on the high side, or the hot side of this transformer, you've got another winding here which is rectified there to there, and this must be the plus voltage output on the transformer, and whatever's, that's the plus there. There's a pen, that would be a good idea. Kingdom for a pen, anybody? Blocks. So that's your plus rail. Need a smaller pen, don't I, really? There's the plus rail going down there. Going to where exactly? I suspect. Let's put my meter on jobby. Put my meter on conductivity test. Put the meter over here next to the microphone so you can hear it. God, I'm good to you lot. Right, there we go. You don't need the meter to hear a beep, do you? No, you don't. There we are, lovely BP. So this there, which is our plus rail, must go down to somewhere down here. Collector. Right, okay. So that's plus rail, and then plus rail going to the collector. The base, is it EBC? Oh, maybe that's the base. No, it's not. That's the base. Base, emitter, collector. Yeah, so we've got an emitter follower down here, presumably. It's my probe slipped. Yeah, there you go. So that is a supply rail up there. Presumably the relay goes to the supply rail as well. And that's a return run from the relay, isn't it? From the coil, or is it? Supply rail, emitter. So it's an emitter follower. The base is driven via that. That's the connections for that thermal switch on the heat sink. So if the heat sink overheats, the base of the connector is disconnected and the relay will be turned off. That's basically it. And there's a couple of 820 ohm resistors in series with the relay coil, 820, so that's 40 odd ohms. Why would you do that even on the relay coil? Don't know. Anyway, so the bottom line is that this is on all the time. It should produce probably 12 volts on there, which goes down there, which goes to the collector of the transistor. The transistor is rigged as an emitter follower. So the collector goes to the plus 12 volt line through the relay coil to ground from the emitter, and then when the voltage gets onto this to bias it from somewhere, there presumably is the input bias to the gate. Look, and there's a pull-up resistor and a capacitor and a 2.22k versus a 22k, right? So this must go. This is must be the control coming from somewhere up here somewhere. Presumably one of these optos, I would have thought. Here, one of these optos is a channel to switch the main power on. Remember, when this is on, that transistor turns on the relay, and then we get the main AC power going into the main bridge rectifier, and then the actual main power supply will start up. So from here must go down here somewhere to one of these two opto isolators. Nope. Yeah, there you go. So that's your standby one. That's the standby. Right. Can you hear that beeping? Right, so we've sussed it out basically. This chip powers up the TMY 274N. 274, 247. 274. Something like a 6-watt power supply. And produces the 12 volts here, which is still in reference to the live side, produces a 5 volt here, control the electronics. There's a standby pin, which is that one there is a standby pin, looking at the other board. And that when that goes, the controller puts that high, it probably uses this transistor here to drive this, which then switches that, which then provides the input to the transistor, turns this 80 volt transistor on. I don't know why they've used an 80 volt transistor, because it's not 80 volts on it, it's running from 12 volts, isn't it? And then that closes the relay then puts the main power onto the main amp, and happy days, everything is on and you're ready to listen to your music. Or are you? So what else have we got? There's a rectifier diode. What's that diode there for? I'm not sure what that's. DW diode. W. I don't know what that is for. It's between 0 volts. It's not a buck regulator. Between 0 volts and somewhere else. Oh, it's feedback. No, it's not. Because that's a plus rail, and you've got 22 k ohm resistor coming down through that diode. So there must be some kind of voltage reference. I'm not sure about that, to be honest. It doesn't seem correct to me, but what do I know? I don't know much. Anyway, so now all we haven't really reverse engineered is what these things are here, right? That thing going from there, possibly to there, to there. We did look, didn't we? I think, yeah, it's a TVS diode. That thing there. That was the yeah, we'll look at the price. P6KE200, I think, 200 volt transient suppressant diode. More and more people are using these in switch mode power supplies, but they get it wrong. There's just so many failing. They get it wrong. And then it looks to me, I'm really interested to know the part number of this diode, because this is supposed to be a high speed diode. Yeah, it's a 4AA1. They've used an ordinary silicone diode. Bloody idiots if that's the one, because the snubber network without the capacity RC, they use a cheap snubber network, a TVS diode and a normal diode and a capacitor, and it's just a cheapskate. Possibly in the right circumstances can give you much better protection, but also in the wrong circumstances, like everything else, is not implemented properly, you're going to have a bit of a problem with reliability, especially because TVS diodes do not like heat, and I'll explain that to you in a minute probably. So what have we got? So let's just measure those diodes, shall we? See what we got. So we're going on diode forward continuity. I better rig the camera up so you can see what the hell I'm doing, to be honest. Hold on. There we are. I need a bigger bench. I've got too much crap around here. I've been working all day on something else, and I thought I'd do a bit of entertaining video work for the Repair Café. When you've looked at this, you'll be able to fix half the power supplies that are out there, or even more. The trouble is, you see, when you fix things, you're not really fixing them. You're making them go for a little bit of time because you've just reassembled the unit with the original design fault in it. And this is probably switch mode power supplies. It's just awful. The amount of the skill level is abysmal, to be honest. And the data sheets are even worse. They don't really tell you how to make a reliable power supply. What do we want? We want the meter over there. When do we want it? Now. Lovely. You can read that, can't you? Where are we? Thought it's worth having a look at the data sheet for the TMY274 series of power converters. It says, the first thing I take umbrage with is efficient offline switcher. Now, an offline switcher definition, as I understand it, is that reduces the mains voltage, but the output is referenced to the mains voltage as an offline switcher, which is kind of counterintuitive, and I think they've got confused here. But an offline switching power supply maintains the relationship with referencing the voltages to the mains, and it's for things like light bulbs and other sealed devices that don't have a switching transformer or don't have the ability to isolate the main side from the low voltage side. You can see you've got a transform here. So this is definitely, in my book, what I understand was taught is not an offline switcher, but maybe they've changed terminology. Let me know, make a comment in the comment below if you can. I'd like to know. So there's the sort of overview of the architecture of the devices. You've got a table here which is showing the family of devices. Ours is the 6-watt 274 at 230 volts AC. It's giving 6 watts in an adapter, i.e. in a sealed plastic case, in an open frame 11 watts peak or open frame. So peak power on the adapter is 6 watts, or if you're an open frame 11 watts constant. And if you're running at 80 to 265 volts up here, you can see you've got up to 8.5 watts in an open frame. So that's where we're at, really. We're not running at 230 volts AC, even though that's the voltage specified on the back of the product. Ours on a UK mains will be 240 to probably 260 volts AC, which is going to be up here. So we could go up to 8.5 watts. And you can see down here the 2NY 280p will go up to 28.5 watts. It's interesting, isn't it? Look, this one, the 274 will go up to a higher wattage at 265, but the 280 will actually be a higher wattage at 230. It's got 36.5 watts down here on this part, and then at 265 it's 28.5. So it's not consistent across the whole family. That's the only thing you need to well, I'm not going to go through the details. I'm going to put the link to this data sheet down in the description if you want to see it and read it. There's the architecture inside. The source has got 4 pins here, look, for cooling issues, so that we can actually conduct the heat away from the package generated by the FET and the online switching, and dissipate it on copper on the board. And then you've got 3 other pins, look. Enable under voltage pin, so you can use that for turning the unit on, the power on off, and also for setting an under voltage limit, at which point it shuts down if the input voltage is too low. And the BPM, I think, is bypass multifunction pin. So it's a multifunction, so that's probably current and voltage regulation, I should think. So here's the description of the bypass multi-pin. You can set the current limit with the capacitor, you can do the voltage, you can do the under voltage cutout and all that sort of thing. Any info, if you want to know something specific, then make a comment. And then all the description and everything else of all the gubbins inside. As I say, the link to this data sheet is in the description, so you can just look it up and read it at your leisure. That's a schematic from the data sheet. And don't design something based on the data sheet. You really have to understand how to actually test your power supply, and to make sure in particular this thing is protected and that it's running efficiently, i.e. if you design it in an inefficient mode, for example wrong capacitor or wrong resistor here, you're going to get a lot of heat dissipation in your snubber at high voltages, and also if you design it incorrectly you'll get an over voltage situation at high input voltages. This is 85 to 265 volts AC here, it says. Here's the actual power supply. If you want to see how this works in more detail than I'm going to explain, then look in the data sheet. But the area of problems we have here is with this TVS diode up here, this one here. And you can see when the actual power supply flyback goes above. Yeah, just to explain how this works, is you've got your transformer here. This is rectified mains sitting at 300 odd volts DC through the transformer primary down through to the switching device, and the way of energizing this is by switching and releasing single-ended. It's not on a bridge or anything, it's just switching on and switching off the current through the transformer, transferring power because of the changing flux in the transformer to the secondary side, and this side here, which is a power supply for the unit. Now when you turn the FET off quickly, the parasitic inductance in the transformer, which I'll show you in video number 2, the magnetic field in that inductance in that part of the core will collapse, inducing a very high voltage, or potentially very high voltage, on the secondary. And so this point here, when the FET turns off, this point here will go on an excursion above the supply rail. Now as that goes above the supply rail, this diode down here will start to conduct and charge this capacitor via this resistor. So some of the energy will be stored in the capacitor, and some of it will be dissipated as heat in the resistor. And you have to choose this selection. A traditional one would just have the resistor and the capacitor, and you have to choose a selection of these components to match the frequency of the ringing in the transformer, and also to limit the actual maximum voltage you see on this point here. And of course the maximum voltage will be here when you're on full load from the secondary side, and you've got the maximum input voltage. So you have to kind of start off with a lower input voltage, start tuning this up, and then selecting your components, and eventually try it on full power, full input voltage. If you don't, you'll just blow up your FET, and you have to change the electronics out and then start again with the development. So they decided that TVS diode is an easy way to go. And the way this works is that if the voltage, the normal stubber network, can't cope with the high input spike and a very high input spike as well, a high voltage spike on here basically, which would maybe destroy or weaken your FET in your device, then the TVS breaks down at 150 volts above the supply rail very quickly, and then we'll conduct that spike directly into the snubber, i.e. this capacitor, and dissipate the heat in this resistor. Now this resistor here is not normally used. If you've got an ultra fast diode here, you don't need to use that. That's just to dissipate heat while this diode is switching off, and is intended to allow you to use a cheaper diode in your power supply rather than an ultra fast switching diode. Our design, we looked up, does have an ultra fast switching diode there, so they've omitted this resistor and they've made this 200 volts. So it's not compliant with the data sheet, but that's not unusual because the data sheets don't really always tell the whole story, not if you want a reliable device. Okay, so they seem fit to make this into 200, but something is not right about this design in our unit, because our TVS diode has blown up. Now you can either conclude that it's a dodgy diode, but if you think about it, when the TVS diode is conducting, it's got 200 volts on it. That's the voltage that it maintains, so a few milliamps going through on a constant basis will make it heat it up very, very quickly and destroy the junction. So either it can't be destroyed by over voltage because it breaks down, so it can only really be destroyed by over current. All right, so that's the weakness of the TVS diode, and I've seen so many power supplies with blown up TVS diodes, and clearly this part of the circuit is not working properly. Otherwise it wouldn't have blown up. You could say, okay, some diodes are crap, but it was an on-semi diode we had, and it was destroyed. So in video number 2, I'm going to redesign do the test on this and do the measurements and conclude whether this is a good design or not, and maybe, if required, change the design of the snubbing components to suit UK mains, which many things aren't designed for UK mains. It says on the back of the product 230 volts AC. We know it's much higher than that most of the time, so straight away this product has got a specification issue. There's a lot of leave a comment down below, but there's obviously the UK main specification has been reset to 230, but the product should really have the maximum range of minimum and maximum voltages that the unit can stand, and it's got to stand more than 230, because our UK mains, generally most households, is quite often 245 and 250, 260 sometimes. So anyway, ranting about the mains voltage, not going to get us anywhere. And then you've got all the other information down here in the application example. And then finally, if you need more information, I'll put the link to this document down down bottom, and this one is the application note for the tiny, it's a engineering prototype report, okay, and it goes into all the detail there. And you might, if you are interested in learning how these things use, like the conduct EMI and all the other issues related to power supply design, which has been a bane of my life, have a look at this document, because you can see very clearly laid out is the power supply, which the TNY, this is a 278 PN, so it's the more powerful version. with a slightly bigger transformer, I would say. But you know, you've got all the basic things there, and then the actual schematic of the evaluation board. You can buy this board as an eval board. It costs you probably about 70 or 80 quid from Power Integrations. But if you were developing a power supply for a product like this radio, you would probably buy the eval board and then work through this and make sure you understand it, and then afterwards, subsequently, when you have your own switching transform and your own design, you would apply the knowledge that you've gained from this particular application note. And it even tells you how to wind the transformer and the number of windings. You see, you've got the windings there. So a very useful document if you're actually thinking of making your own power supply. But even if you want to understand about these and what can cause problems, then it's a useful document. Now the question is, did the radio engineer read this? If you're his director or his development manager, I would swap up on this. When I used to run the development department, or I'd look at the data sheet of the things that they'd actually designed something with, read the applications note, try and understand what's going on, and then quiz the engineer to find out what testing he's actually done to make sure that all these components are running and running happily. There's even a heat map of the board there. Look, there's the secondary rectification diode, which is often one of the hottest. There's the actual IC itself. Very interesting document. Links below. Read it. Any comments you got, questions, put them in the comments of this video and I will answer it. So anyway, we're going to move on and release this video now. And if you're interested in the secondary engineering investigation as to why this failed, that's going on in the second video in this playlist. Back to the main video. Right, I've had my tea. I think it's time to start poking about with the meter. Yeah, so we've got our meter probes and we're on forward diode continuity test to test out some of the semiconductors to start with. Put the display up for you. I think you can hear it. Yes, you can. Yeah, so let's have a look at the main rectification diode down here for the 12 volt rail. 500 millivolts. Open circuit, well, effectively open circuit, so the rectifier diode's okay. Let's check this diode down here, the one we're not sure what it does. We'll look at the schematic in a bit. 600 millivolts. And 2.5, okay, so that's working, that diode, as far as we can tell. The other thing that may have blown, an overcurrent situation, although I wouldn't expect it to start up at all, would be this 1 ohm resistor down here, the actual current sense resistor. You can say it's saying 1 ohm. So that resistor is okay. And what else have we got? We've got the snubber network devices. On the back here, there are two diodes. A 200 volt. Back here are the two diodes. There's a 200 volt TVS diode, transient suppression diode, and a standard IN400. One is that? That can't be right. I said that before. This should be a high speed diode, otherwise it won't turn off in time and it will dump lots of power into the protection device. So we could be looking at a design fault. So we'll look at that. We'll investigate that in a minute and see what they've done. But anyway, we've got our diode. We've got our main TVS diode goes across here, and we've got 460 millivolts is about right, and then reverse. That shouldn't be conducting. That's breaking down, isn't it? A normal TVS diode will, when it's forward biased, will just give you a normal junction, and then the reverse bias at the working voltage will give you 10 microamps or something. So this, somewhere here, there's something happening that shouldn't be happening. So the TVS goes from there to there. Yeah, definitely looks like that's an odd voltage. And then there's the other diode goes from here. That's a normal diode drop, and you've got the 800 millivolts again. That's because of this path back through the transformer primary, because that point there is 0 volts. Yeah, so I'm not sure but it looks like we've got a short TVS diode. I'll just take the diode out, shall I? And let's have a look at it. Cutters. Cut that wire there, should be able to get it to drop out. Soldering iron on, should have turned that on before. Yeah, if you have got one of these Weller irons, here's the iron there, just make sure when you first put the bit in, if it's cold, you tighten it up, and then because this is at 370 degrees or something, that tube gets longer, and then you'll find that the bit isn't being pressed onto the end of the flat end of the soldering iron heater element, which is there. So must remember, especially if you're doing things that have got a lot of thermal capacity, you know, like big heat sinks and things, you must remember once it's heated up to pinch that down, otherwise if that tip isn't pressed firmly onto the actual heating element, you don't get a good thermal transfer. Right, what we're doing, oh yeah, we're taking, yeah, it's fucking digressing here, baby. We are removing the suspect TVS diode. So I'll grab hold of the end of it with my cutters, and then we'll give it some heat. Is it that one? Yeah, it is that one. Good guess. Yeah. So here it is. Here's the offending device. P6KE 200A. So on these TVS diodes, they're all pretty common. The A means that it's a single directional. It'll only break down in one direction. I think the B or the Y, if it's not an A afterwards, they're usually double-ended. So there's two TVS diodes back to back. So they will protect the voltage in any polarity, positive or negative. But they're in series, of course. P6KE 200 stuff. So 200 volts. This should be like a normal diode until the voltage at that point gets 200 volts more than the voltage on the anode, and yeah, it will conduct, and then away you go. Basically, you get very good conduction, and they turn on so fast you can hardly measure it with the scope. I mean, I tried to work out what the turn on time was once, but it's like nanoseconds. Incredibly fast protection devices. They're very good, but they don't like heat. They don't like repetitive discharge or dissipation in them, because you've got 200 volts across here. So if this is discharging, it doesn't go short circuit, it clamps. So if you've got 1 milliamp at 200 volts, you've got quite a lot of, for every milliamp, you've got quite a lot of dissipation. So they will get hot quickly, and they will burn up and blow up quickly. So in this direction, we should have a normal diode, which we have, so that looks good. But in this direction, oh dear, oh dear, oh dear. Let me just go and get, I've got some of these in stock. I've got about 10 different types. These are the same, I think. I've got so many parts now, I keep them in filing cabinets, filed under the part number. Same size? Well, immediately you can see it's actually quite a bit smaller, but it's got P6KE, P6K. Yeah, so I mean, it's suspicious that the package is smaller and the leads are a lot thinner. That tells you something, doesn't it? And yet they've got identical part numbers on it. So looking at that, I would be alarmed, because these things are heat sensitive, as is given by the thick, possibly silver leads or whatever they are, but they're not copper inside, are they? And they're not iron, I don't think. Yeah, so the body of this thing is much, much bigger. So it suggests to me P6KE 200A, great chunky device. And this is a P6KE 200A. So what's going on there? Look at the relative size of these two. This one, I imagine, would be very sensitive. So it's probably a shitty Chinese part, sorry my French. But anyway, let's have a look and see what we get on this one. So just comparing the two of these in terms of conductivity in the right directions. This is a brand new diode that's giving 569 millivolts one way, and it's open circuit the other way. This one is shorted, so that is gone. So we have a blown up diode, but we have replacements which are frankly quite suspect, because the power dissipation of these things is going to be dependent on well, one of the things is going to be dependent on the ability to conduct the heat away to the board, and that's what those great thick leads are compared to the little legs on this one. So if this is a P6KE blah blah blah, it is something fundamentally different about it. Okay, so let's put them over there, and let's get back on this again. We'll just check that other diode in there that we've got. So there is another diode there to there, I think, and now that is a diode. Okay, so they are these. It's the only one that's showing these low test voltages is the TVS diode is blown. Okay, now we could just replace that TVS diode. There's two things about it. Is many designs with TVS diodes in haven't been done properly. I don't know whether it was expertise that was developed after the release of the data sheets, or whether it was a very early TVS design, but I can tell there's a problem with this. And if I just change that diode, especially for this little pox little one, it'll work for a while, but maybe you'll get a high mains voltage coming at this end, and then you're back to square one. You've got a blown up TVS diode. I am going to, because the TVS diode is in the stubber circuit, and this has been switching the snubber circuit, and the snubber circuit, it's actually had a short on it. I'm going to change the TNY 274PN. I'll change that chip anyway, because likelihood if it's not destroyed, it's been strained. And then we need to decide what to do about this diode in here, because if I'm not mistaken, I'll just snip the top of that one. What is it? It's a 1N. Don't believe that. I'm going to take that out and have a look at it. Is that it there? Okay. Got that out. UF4006. UF4006. Let's have a look at that on that screen. Here's a data sheet for our diode. Hopefully it's an ultra fast one. It says UF. I presume that means ultra fast. 4001 to 4007. Ours is a 4006, so we've got 800 volt working there. 800. Twing, twing, twing. 800. And what's that bit over there then? Okay, that's just the packaging. Power dissipation is 2 watts. 4006 has got a 1.7 volt max forward voltage drop at the rated current, and it is, because it's a higher voltage one, it's a 75 nanosecond turn off, so it's a tenth of a microsecond, which is not ultra fast. It's quite fast. It's fast enough. It depends on the frequency of the switching of your power supply, and also the frequency of the ringing on the transformer when you actually in flyback. So yeah, it's a fast diode, so I guess a resistor is not needed. Doesn't say it's called UF but not ultra fast, is it? So that's interesting. But anyway, that's the diode. It's okay. It was a TVS diode that failed, so back to the main video. Yeah, I'm a bit worried about this. The relative size of these diodes and those leads, they've got exactly the same part number on, but clearly something is not quite right. P6KE200A, and this one is an on semi. I don't know if you can see that, it says on semi on it, on the semi perm, and this one's like nothing, ting pong. So, you know, I'm very worried about. I'm half tempted actually to get the current probe and the dev kit out and just do like a couple of hour exercise on this board to fit a standard snubber network. But to do that, I'd have to rig the scope up to it, take some certain measurements at peak output, and then calculate the actual component values for the snubber capacitor and the snubber resistor. We've got a diode in there already, so we could replace this with a capacitor and a resistor, and even possibly leave that in place and have a conventional snubber network rather than one of these new, oh dear, there's been a bit of an incident, I'm going to blow up. You think, you know, this stupid design fault in an obvious place, and the bloody the radio's not working. The customer's almost lost radio. So what to do? I don't think what I'm going to do. I know what I'm going to do. I'm going to put the new diode back in, and then I'll hit this with 275 volts or thereabouts, and we'll see how hot the diode gets. And if it works okay, I'm gonna conclude this video, and then if you want to see part 2, which is the designing of a proper snubber, so it's something about switch mode power supply design and also rectification of this design, which is clearly unreliable. As I say, I've seen so many of these things with the TVS diode blown. It's just a mistake in the design. So yeah, I'll put the diodes back in, get it working, so we can demonstrate that actually it's fixed and it'd be a straightforward line to the fix. But in the next video, I'm going to do the development work, if I get a moment, on series 2 of the playlist for this particular repair, where we take that out again and we fit a standard, I suppose you'd call it traditional snubber network onto this to work, and I'll show you how the snubber network is calculated and how the measurements to take if you are designing a power supply. So a bit of a design video next time. But anyway, there you go. So let's just get me put those parts back in, and then we will see how it goes, see if it works or not. So get the flux out. Last, I've got some flux on the go. They are. There's one lead left in there, isn't there? Which is that one there. That big one right next to the transformer. God, you think about the amount of stuff that's ended up in landfill from bad switch mode power supplies. Clearly, you know, the people that design PC power supplies, you know, for personal computers and things like Panasonic TVs, they clearly know what they're doing, those guys. Because they hardly ever fail, do they? And I don't understand why there isn't a go-to cheap power supply company that makes high reliability power supplies. I mean, it looks like they've taken a reasonable amount of it, taken reasonable precautions, but I think they may have got this wrong. Did that come out? No, it didn't. Grab hold with the tweezers and give it a pull. Honestly, if I was in government, in the Department of Trade and Industry, what they call it, I'd say that every product that has a switch mode power supply in has to be appraised by me or someone like me to say it's a worthy device to be connected to Her Majesty's mains, because this is a serious problem which is causing serious pain to consumers and serious pain to the environment, and probably poisoning me with sulphur fumes, constantly having to repair the bloody things. It's been held on by silicone at the moment. There we are, there's the other lead. Get the mother sucker on it. Yeah, suck that one off a treat. Right, I'm just going to put these diodes back in. I'll join you when I've got them back on, because I've got to go and do something. Hi everybody, so I put the TVS diode and the fast silicon diode back in, the new TVS diode, the new mini one, the less butch ones, and the slightly effeminate one. In there, and I also changed the power supply chip, although that wasn't the fault in the first place, but I've changed it because it might be, as I explained before, weakened. Alright, so you saw the changing of it earlier in the video. So yeah, it's plugged in, and we're looking for a nice clean pudunk when we turn it on. Ready? Contact. Yeah, did you hear that relay go click? So it's clicking on now and staying on. There's a light on around there as well. There you go. So the first click is my main switch. Switches the relay on automatically, and then second click is my main switch going off, and then click from the relay. So it's mended now. I'm pretty confident it's working. It was the diode. We found it with a meter. To be honest, it wasn't that challenging, because if you see one of these cheap single chip integrated power supplies with the minimal amount of components around them, that have been designed based on the simple information, that, should we say, the idiot's guide on the data sheet, because that's all the circuit diagram on the data sheet is the idiot's guide, but most of these people replicate that totally, and there's a few key things they've left out. So it's working. If you want to see how, I'm going to replace that snubber network down there in part 2 of this video with a traditional RC diode, so a diode, resistor and capacitor snubber network. We have to set it up and measure some impedances and some we have to measure the parasitic inductance for the transformer. We have to be able to monitor the actual transformer primary current, and we've got to work out a way of monitoring the actual transformer connection excursion voltage, maximum peak excursion voltage, and to an extent the frequency of the ringing afterwards, because we've got to design a snubber which will protect the device, the actual FET in there, to stop it going over its design maximum voltage. In fact, we want to get within, say, 70 or 80% of the design maximum voltage to give some headroom at 245 volts input, don't forget, because this product is only spec'd for 230 on the label. So it's incorrectly spec'd for the UK actually, although the UK is officially 230, but they only did that to drop in line with the European Union. They didn't change anything, they just changed the specification to plus 6%, which goes to 245, 246, and minus 10. 230 volts minus 23 volts, so whatever that is. 207 volts, really? Yeah. Yeah, so if you've got 207 volts come out your mains, you're still in spec. Alright, so anyway, so we've got to use the clean AC power source. Got an electronic solid state power source that will go up to 350 volts AC at 500 watts, so we can exercise this. When you turn the voltage up, get to maximum operating conditions, and then design the snubber. Right, do that in part 2. If you're interested in design, you're interested in finding out what goes wrong with these, it will give you a good insight into what's happening down there in that in these switch mode power supplies. And if you liked it, hit the subscribe button and leave me a like, and if you didn't like it, well, bugger off and watch a different channel. Thanks so much for watching.